Let's look at example 4. Shown in the figure, you have a rectangular steel bar that is connected to a C channel. What happens is a force of 16 kilonewton is acting, and we've got our 4 bolts A, B, C and D. So whenever you're given this type of problem, the first thing that we need to do is we need to see where our centroid is. So when you look at this question, you'll see that the distance from O to B is 120, distance from A to D is 150, and when you look at the centroid that is given, it is right at the center of this bolt pattern. And then what we can say is that the bolt pattern is rectangular in nature. So for a rectangle, the centroid is right at the center of the rectangle itself. So it is at this particular location, is indicated as O over here. So the next thing that we do is we need to see the distance of the centroid from the point of application of this force F. So when we look at the distance is simply equal to 300 plus 50 plus 75, that is simply 425 mm. So we know 16 kilonewton is acting, and in order to calculate the moment, what we do is we always calculate the moment about the centroid. So this moment is going to act in the clockwise direction about this centroid O. So we've got a clockwise moment, and then we calculate moment by simply saying that force times the perpendicular distance. So force is acting in the negative y direction and the magnitude is 16 kilonewton, and the distance from the centroid is 425 mm. So this we'll use to calculate the moment about the centroid a little bit later. And then what happens is your direct shear is 16 kilonewton, and we've got 4 bolts. So with this we can calculate our primary shear. So we have to calculate the resultant load on each bolt, calculate the maximum shear and the maximum bearing stress. So what happens is, once we have located our centroid, as I mentioned earlier, what we can do is, we know that the value of V is 16 kilonewton. The moment, as I was mentioning earlier, the force was 16 kilonewton, and the centroid was located 0.425 meters away from the point of application of that force. So 16 kilonewton times the distance DC, which we calculated over here, in order to calculate the moment about our point O. So moment our point O is 6800 Newton meter. Now the next thing is to calculate the distance of each bolt from the centroid. So we'll see that bolt A over here and the distance of bolt A from the centroid. So this becomes the distance of bolt A from the centroid. This becomes the distance of bolt B from the centroid. So this is RB. This is RA. So when we look at the geometry that is given to us, the distance of bolt A horizontally to the centroid is 75 mm, and then distance of bolt A vertically from from the centroid is 60 mm. So this distance RA is nothing but 60 squared plus 75 squared, out in square root. So the distance of bolt A from the centroid is given as 96 mm. So when we look at the bolt pattern that is given to us, it is symmetric. So we can say that bolt A is located 96 mm away from the centroid. B, C and D, bolts B and C, D are also located at the same distance away from the centroid, just because looking at the geometry that is given to us, because D is also 60 mm away in the vertical direction away from the centroid, and so on. So now with the given loading scenario, we know our centroid is over here. We have calculated our distance RA, RB, RC and RD to be equal, right? The force is acting in the negative y direction. The distance of the centroid O from the point of application of this force is 425 mm. The moment about point O is in the clockwise direction, because application of F will cause a moment in the clockwise direction about O. So first thing, we can calculate our primary shear. So primary shear is calculated using this formula, V over N. V was given as 16 kilonewton, N is the number of bolts. Number of bolts was 4, so your primary shear is 4 kilonewton. For secondary shear, we can calculate our secondary shear using this formula. So F double prime n is equals to M1 Rn divided by Ra squared plus Rb squared plus Rc squared plus Rt squared. Now what happens is, let me just calculate the secondary shear that is acting on bolt I. So instead of n, it will become I. So F double prime I is equals to M1. Instead of Rn, I am looking at the distance of bolt I from the centroid divided by Ra squared plus Rb squared plus Rc squared plus Rd squared. So now substitute everything. So moment was 6800. Distance of bolt I from the centroid was 96 mm. So convert everything to meters. Due to the nature of the bolt pattern that is given to you, all the bolts are located at equidistance from the centroid. So that's why I have 0.096 squared appearing 4 times. So once I do this calculation, I get my secondary shear to be 17.71 kilonewton. Now what happens is, since all the bolts are located at the same distance away from the centroid, so what that simply indicates is the secondary shear acting on all the bolts are exactly the same. So again, secondary shear on bolt B, C and D is same as secondary shear on bolt I, which is 17.71 kilonewton. Now what happens is, the next thing is that you will draw your bolt pattern. This is not drawn to scale. You will draw your bolt pattern, you will draw your location of the bolt, so I, B, C and D, and you will represent both the secondary and primary shear for each bolt. So what happens is, you've got your bolt pattern. So you've got your bolt pattern. Then what you do is, you draw this lever arm to get your centroid. So this is my lever arm and this is my centroid. I know that the moment about my centroid is in the clockwise direction. So your primary shear acts in the same direction as the applied load. So your applied load was acting in the negative y direction. So you'll see that on all these bolts I, B, C and D, I have represented my primary shear. For instance, F prime D, F prime A, F prime B and F prime C to be acting in the negative y direction, in the same direction as my applied load. But this is 4. So done. The next thing is, I will represent my secondary shear. The manner in which I represent my secondary shear is very, very simple. If this is my lever arm from O to B, your moment is force times perpendicular distance. Now what happens is, you know that your moment about point O is in the clockwise direction. So on this lever arm, I have to represent a force which is going to cause a moment in the clockwise direction. So if I apply a force in this direction, you'll see that the moment about this lever arm is going to be in the counterclockwise direction. So that's wrong. So that's why my secondary shear at B is in this direction. So again, force times the perpendicular distance. So this is at 90 degrees. So this force acting about this centroid is going to cause a clockwise moment. Now let's look at I. So for I, the lever arm is from O to bolt I over here. So now I need to have a clockwise moment. So only way I can get a clockwise moment is if my force is acting in this direction. So therefore, that's how I will represent my secondary shear at bolt I. Now moving at bolt C. Again, lever arm from O to bolt C. Moment has to be clockwise. So this is the only way this force is going to cause a moment in the clockwise direction. And at D, this is the orientation of your secondary shear which will cause a moment in the clockwise direction about your centroid O. So once we have that, it becomes a little bit easier. The next thing is, we will calculate our resultant FI, FB, FC and FD. So that's the next part that we need to look at. So what happens is, the resultant force is calculated using cosine rule. So what your cosine rule says, that the distance or the length C squared is equals to I squared plus B squared minus 2AB cos theta C. So if this is the length that you are looking at, this is the side, then the corresponding angle is theta C. So we'll use our cosine rule to calculate our resultant forces. So now what happens is, I am just looking at bolt I. So at bolt A, I've got my primary shear which is acting downwards. This is how my secondary shear look like. So my resultant, whenever you add your vectors, add them to head to tail. So this is the resultant, and I know that this is the value that I want to calculate, Fi, and this is the corresponding angle theta. So the first thing is I need to calculate my alpha. So with respect to the bolt pattern, I can calculate alpha quite easily. The horizontal distance 75, the vertical distance is 60. So alpha was tan inverse of 60 over 75, which was 38.7 degrees. Now what happens is, you'll see that if this is 38.7, so this one is 51.3. Again, you can find your theta, or simply what happens is, if this is 38.7 degrees, we know this is a right angle. This is a right angle as well. So theta is simply equals to, theta is simply 360 degrees, since complete circle is 360 degrees. So theta is equals to 360 minus 90 minus 38.7. You will get the angle equal to 141.3 degrees. So substitute. So primary shear was 4 kilonewton, secondary shear was 17.71 kilonewton. Substitute and you will get your Fi as 21 kilonewton. Fi is same as Fb and Fc will be same as Fd. So that's why I'm not calculating Fb. Now in the similar manner, what I have is I have Fd. So this is my primary shear, this is my secondary shear. Again, alpha is calculated using tan inverse of 60 over 75, which was 38.7 degrees. Now what happens is, this time around, this is my Fd and this is the angle that I am interested in. So if this is 38.7, I know that this is a 90 degree. So this angle over here is 51.3. Now what happens is, this again becomes a 90 degrees, and then theta is same as alpha, so which was 38.7. Substitute everything into the equation once more. Your primary shear is 4, secondary shear was 17.71 kilonewton. You will get your Fd as 14.8 kilonewton. So again, once more, to calculate your angle, you can use this is not drawn to scale, right? So you need to understand as to how you can calculate your theta. So please do practice. So look at trigonometry and see how this angle was calculated. Just don't follow me that okay, this is always going to true. I can simply change the bolt orientation, the pattern, and things will change, and you need to understand how to calculate that angle theta. Finally, what happens is your maximum stress. Now once we had calculated that the forces acting on all the bolts, so force D is same as the force or the resultant force acting on bolt C. So between this, the maximum force was acting on bolt A and bolt B, which was 21 kilonewton. So your maximum shearing stress is nothing but Fmax divided by the cross sectional area of the bolt. So your shearing stress, the cross section that we are looking at is basically the cross section is a circle, and we know that the bolt was M16, so which has a 16 mm diameter. So the area is calculated using pi d squared. So 21 kilonewton divided by pi d squared, you will get your shearing stress as 104.45 megapascal. Now for maximum bearing stress, the channel is thinner than the bar. So the channel had a width of just 10 mm. So that the largest bearing stress is due to the pressing of the bolt against the channel web. The bearing area IB is simply the thickness of the channel times the diameter of the bolt, which was 16 mm. So 10 was the thickness of the channel times 16 mm, which gives you 160 mm square. Thus what we can do is we can calculate our bearing stresses. Your bearing stress is nothing but Fmax divided by bearing area, which is 21 kilonewton times 10 mm was converted to meters, 16 mm was converted to meters, and we get your bearing stress is 131.25 megapascal. So this diagram actually indicates what your bearing area is. Imagine you have a bolt that goes through this. So when we look at from the side, we'll see that okay, we see this, and when we look at from the top, the area, the bearing area is simply this, and this bearing area is basically the thickness of the channel times the diameter of the bolt. So that's what we have over here.